Okay, hello. My name is Sara Wichman. I'm a PhD student at the University of Washington. I work under Professor Jeff Berman on the NSF-funded Tallwood project. And today I'm going to be talking about some dynamic testing that we did at the UCSD shake table of cross-laminated timber rocking walls. And then I'm going to talk about some of the modeling that we've done since then. So kind of the motivation for our project is that urban populations are growing quickly and we need to start building up instead of out. And we kind of need, there's like a need for 8 to 14 story mixed use buildings that can be built quickly. And there's kind of a need for a material that's more sustainable than concrete or steel. And we believe that creating a system using glulam and CLT panels, we can achieve a system that's competitive to steel or concrete while also reducing our CO2 or our carbon footprint of our building by about 60%. So the overall goal of our project is to develop and validate a seismic design methodology for tall wood buildings. This is a fairly large project with quite a few universities. This is kind of our overall project outline. We kind of do some sub-assembly testing to create some models and develop a design methodology, and this is all to validate, and then this will all build up and we'll validate all of this through a 10-story shake table test at UCSD in the summer of 2020. I think we'll be the first test on there with the updated table. But today I'm going to talk mainly about the 2-story shake table test that we did, as well as the modeling. And I'm going to focus mainly on the walls. I'm not going to discuss much about the gravity system or the diaphragm. So these rocking post-tensioned walls, they're post-tensioned at the base, and this provides the recentering capabilities. And then we have UFP energy dissipators. Kind of any energy dissipating device could be used. We chose these. They just simply yield to dissipate energy. And that gives us a hysteretic behavior shown there. It's kind of flag-shaped, it recenters, as well as dissipates energy. So first I'm going to talk about these tests. Here's a picture of our specimen. It's 2 stories tall. First story is 12 feet, second story is 10 feet. It was 20 by 58 feet, or kind of the diaphragm square footage. And we had 2 coupled CLT shear walls in the middle. And if you look in the picture in the upper left-hand corner, we wanted to kind of increase the footprint of the shake table. So we put the gravity frame on like these extender beams so that we could make the specimen larger. In order to get the walls at the same elevation, we had to put the walls on those blue base beams, which kind of caused some problems, so we'll talk about that later. So the walls, which is what I'm going to focus on, they were 5 feet wide each. They were 5-ply CLT, so about 7 inches thick and 24 feet tall. Each wall had 4 PT bars, kind of 2 in the front and 2 in the back. They were post-tension to 40% of their yield strength initially. And yeah, and then you can see kind of that's them sitting on the base beam. And then at the wall and diaphragm connections, we had some out-of-plane restraints. We kind of put 2 angles on either side to brace it. And then our wall to diaphragm connection to transfer shear, it was kind of like a cantilevered steel plate, which you can see kind of right in here. You can't see that, but a cantilevered steel plate, and it was in a slotted hole so it could transfer shear without transferring moment. So we designed these walls for Oakland, California with a site class B and a R factor equal to 6. And when we designed these, we designed them for a set of performance objectives. We were looking at 3 levels of ground motions. The first we called our service level earthquake, which was 50% and 30-year hazard level earthquake. We also had our design-based earthquake we said was 10% and 50 years, and then we had an MCE. And for each of these earthquake levels, we kind of looked at 4 main things about the wall that we wanted to achieve. The first, we wanted to achieve like a drift limit for each earthquake. So you can see the drift limits. We wanted to stay at under 1% for service level, and then 2% for DBE, and MCE we targeted 4. We also looked at PT yielding. We wanted to make sure we didn't yield the PT bars until the MCE ground motions. UFPs, we wanted those to dissipate energy, so we said those could yield right away at service level. And the last thing we were looking at was damage of the timber, the rocking walls, and we wanted those to have no damage under service level, and then just minor damage under DBE, and then we allowed more damage at MCE. So we'll talk about those things when we look at the results. So we tested 14 ground motions. The last ground motion was MCE times 1.2. We never actually yielded the bars under MCE, so we wanted to scale it up to actually see yielding. So I'll go over the test results. This first video is a video of the MCE test. We reached about 5% drift. This is MCE times 1.2. Here we reached about 5% drift. And after this test, the building fully recentered. I think the residual drift was less than 0.05, which is pretty good. And we actually saw no damage to the walls, which we'll talk about. So I just showed kind of the drift plots for 3 of the 14 ground motions. And then on the bottom plot, I'm kind of summarizing all 14 tests. So as you can see and then I'm kind of reviewing the performance objectives here. So for SLE, we wanted to stay under 1% drift, which we achieved. All of our SLEs are below 1%. For DBE, we didn't quite achieve that. Some of our DBE motions shown in blue went closer to 2.5, but our MC was also within our performance objectives. So this drift was kind of our controlling factor here. Looking at the PT bars, so these are plots of like the 4 PT bars that go across the wall, kind of the left wall, or the left 2, and then the right wall, the right 2. Under service level and design-based earthquake, we had no yielding, which is what we wanted for our performance objectives. Under MCE, we just barely yielded our bars, but that's still within our performance objectives. And then here's a plot of our larger than MCE ground motion where we actually yielded the bars. But again, we met all of our performance objectives. For the UFPs, we also met all of our performance objectives. The way we quantified this, we measured the displacement of the UFPs, and then we predicted what the force in the UFP would have been by using a calibrated Stilo 2 model in OpenSeas. We had tested UFPs prior, so these were just predicted forces. But as you can see, they yielded kind of right of way in the SLE test, but they didn't start dissipating too much energy yet. And then they all yielded about that, so yeah. So the CLT crushing and damage there, we actually had no damage at all after all the tests. You can see a little bit of splintering on the ends, but that was mainly due to transportation of the walls, getting to the site. And you will see here, there's this little gap here. So initially we thought that the walls had compressed a little bit, but when we took the walls off the specimen, it didn't compress at all. So what actually happened here is that the base beam that the walls were sitting on actually yielded and deformed, which was unfortunate. But we had no CLT damage, but it was most likely due to the fact that the beam that the walls were sitting on saw all the damage. So the next slide is going to show a video of this corner here. And you'll see, if you just kind of watch this location, you'll see the whole flange flopping up and down. And it actually went down. So if you look right over there as the ground motion starts, it started off yielded because of from a previous test. And in this test, we actually had downward deformation of over 1/2 inch, which made it very hard to model. So we'll talk about that. But we believe this is kind of what actually protected the walls and why they saw no damage. Okay, so this is just kind of overall hysteretic behavior. So as you can see in this plot of base shear, kind of as we increase our ground motions, we kind of start leveling off. But in general, for our tests, all performance objectives were met. We had some, with the DBE motions, we had some higher drifts than we wanted to, but mostly they were all met. So next, I'm going to talk about the numerical modeling that we did. We modeled this in OpenSeas. We used Timoshenko beam column elements to model the walls, and then we used tension-only truss elements for the PT bars, elastic, perfectly plastic. And then we had, for the UFPs, we kind of had a rigid link connecting a zero length element to model the UFPs. And then at the bottom, we have a multi-spring contact element to measure the rocking. I'll talk about that more on the next slide. And then in attempts to model the base beam, we put another layer of springs, which I'll also talk about in more detail. So the multi-spring contact element, we modeled it with nonlinear. It models the nonlinear rocking behavior of the walls and the compressive deformation of the CLT. So you can see our material model that we used for the CLT, elastic, perfectly plastic, compression only, so that the springs could rock up in tension. There were zero-length springs, and they were distributed in a Gauss-Lobato distribution, which is what's commonly used for rocking structures. So in attempts, we had to model this base beam. We didn't want to bring in shell elements. We kind of wanted to stick with our truss or our springs. So we had to try to turn a shell or the shell into springs. So we kind of guessed there. But this is the beam. The cross section is the double web I-beam. So what we decided to do is we kind of assumed that was like fixed with a distributed load, and then just used plastic analysis in order to get the stiffness curve. And that was kind of our initial guess for how to model this. And we kind of used that stiffness. We distributed it in the same Gauss-Lobato distribution as the multi-spring elements. And we kind of just calibrated it until we got close enough. So these are two of the drift time histories. You can see that the model actually got really close with periods. We're not quite getting the peak drifts that we wanted, but it's still pretty close. And I should note that like the model is very sensitive to the beam stiffness. So if you kind of just change it a little bit, a lot, the model kind of changes a lot. So this differences is most likely just due to not modeling the base beam super well. But we did our best. So our biggest question though with modeling is what would have happened if we actually had a rigid foundation? What would have happened if we didn't use the flexible base beam? So what we did is we just took off all the base beam springs and just modeled it as we would have normally. So here I have plots. The X's are kind of rigid foundation. The dots are kind of the flexible foundation for the OpenSeas model. So the drifts, you get slightly smaller drifts, which makes sense because the beam is more stiff, so you're going to get less deformations or less displacements. So now we kind of meet all of our performance objectives. I mean, we still have the one DBE test that is above 2% drift, but we're a lot closer now. For the PT bars, we got more yielding with the rigid foundation because the wall was actually able to rock up on its corners. So we saw more yielding, but we still met all of our performance objectives, even if we had used a rigid foundation. For UFP yielding, not much changed here. The UFPs yield pretty early, so those kind of stayed the same. And then for wall crushing, this is kind of the biggest one because we saw no wall crushing or no damage to the wall at all. But we wanted to look at kind of how much, what is that crushing length if it was rigid. So the next plot's going to show kind of what is the length of crushing or what percentage of the wall length is going to be crushed. So for the rigid or for the flexible foundation, we had no crushing, no yielding, nothing. But then once we made it rigid, we actually started seeing some damage under the ground motions, which is what we designed for, which is what like our performance objective said. So even though we had more crushing with a rigid foundation, or we would have, we still are within our performance objectives. We're just a little bit less conservative now. So in conclusion, we did this full-scale shake table test. I didn't talk much about the design of like the diaphragm and the gravity frame, But those all perform very well, and it kind of shows promising results for our 10-story test coming up, that we can use similar we can use similar things that we've done. We used a design procedure that I didn't get to talk about, but it resulted in a relatively successful design, and we met performance objectives for crushing, UFP yielding, and PT yielding. The drift is kind of what controlled at that DVE level. And then we also found that our modeling techniques produce a representative model. It is fairly sensitive to that base beam property, and that's kind of what made our model not exact, but yeah. And then we also concluded that this rocking wall, that base beam, is kind of what protected the wall from damage. But we still would have met performance objectives with a rigid foundation. So then I'd like to acknowledge our funding sources as well as all of our sponsors for our test. So thank you.